Okay, making a start. So, first of all, just as a quick reminder, because I know it's been a little bit, if you go on to the website, which the link is in Show My Homework, you will have access to this notes booklet. And I'm just going to fill it out with you guys while explaining these concepts as we go along. So our topic that we're covering today is the P2 topic, which is basically energy transfers via heating. So you covered this a little bit at Key Stage 3. Most of you have probably forgotten a lot of it, but hopefully some of the words you kind of remember hearing and have some sort of general idea in the back of your mind that will be able to bring out. But if you can't remember it at all, no worries. I'm going to assume, I'm going to start from scratch, assuming that you have no knowledge, but you probably will notice that you're coming in with a little bit of background knowledge as well. So, in terms of energy transfers, there are three main types of energy transfers, three ways that heat energy specifically can be transferred. Conduction is one of them, which we're going to be talking about today. You have convection. Conduction, convection. Ooh, why is my pen a little bit wonky? Thickness. We'll increase the thickness. And radiation. Let me just plug my pen in. It might be losing battery. All right. And radiation. So those are the main three ways that heat energy can be transferred. So the first one we're going to talk about is conduction, because there is a difference between these three ways that energy can be transferred. And it all depends on whether we're working with a solid, liquid, gas, or none of the above. So with conduction, when we talk about conduction, we're specifically talking about solid materials. So anything that is solid would conduct heat. Some things are better, though, at conducting heat than others, which is why some things are used to transfer heat a lot better. Like, for example, metals are really good at conducting heat. So we use metals for things like, cooking, frying pans and things like that, because it's really, really good at conducting heat. And when I say the phrase conducting heat, what I mean is that it's really, really good at transferring heat through this method. So we're going to zoom in terms of particles and look at what happens in conduction. Basically, what happens in conduction, how the particles behave, is different to how it behaves in other ways that we transfer heat energy. It's different to convection, it's different to radiation. So when you look at a diagram of conduction, you should be able to recognize, oh, this is conduction happening, because the differences between those three types of heat transfers is on that particle level. So let's get started by looking at this diagram then. So hopefully, just from previous knowledge, you guys would be familiar as to the particle structure of the particle model for a solid. Just as a quick reminder, we have, these individual particles, and they're arranged in rows. They're also quite tightly packed. I put a little bit of space between them in this diagram just to make it a little bit easier to see. But they're tightly packed and in ordered rows. It's incorrect to say that they're just completely not moving, because they are moving, but they're not moving around. They're just vibrating on the spot. So these particles are basically in ordered rows vibrating. Now let's imagine that we heated up one of these particles. So in this diagram, the case of what we're heating up is this bottom left particle here. We're adding a little bit of heat to it. Well, when we're adding heat to a particle in a solid, it starts moving a lot faster, meaning it starts vibrating a lot faster on the spot. I'm going to write that down. For this question, what does heat cause a particle in a solid to do? Is it vibrates faster. The reason why that happens is because we're giving it energy, right? We're giving it energy in the form of heat, so it's going to, when it gets that energy, it doesn't know what to do with it, it's just vibrating on the spot a lot faster. But because it's vibrating on the spot faster, and because in a solid these particles are close together, tightly packed, when it's vibrating a lot faster, it's also smacking into its neighbors, right? So it's hitting the particles that are nearby it. So in this case of the particle in this corner here, the particles that are touching this particle is that one and that one. So what it does is it basically passes on vibrations. Imagine you're sitting on a bus in public transport, and let's pretend that you're squished in the middle of two people. Let's say that you start shaking back and forth really, really quickly. Well, the others wouldn't be able to help, but also start shaking back and forth a lot quicker than they were, just because of that close contact. Which is why conduction only happens in solids. It doesn't apply to like liquids or gases, especially not gases, because gases are like, all the particles are spread apart. So it's not going to be a case of one particle vibrates faster and then hits the other particles that are neighboring. That's not going to happen. With liquids, it doesn't happen because the particles are free to move around, so its neighbors aren't fixed. So that's why conduction only happens in a solid. Now eventually this keeps going, right? We start off with one particle, it passes on its vibrations to its neighboring particles, they start vibrating faster, and then they knock their nearby particles, and then they start vibrating faster, so on and so forth, until vibrations / heat energy pass through entire object. So that's basically what happens. The heat energy will pass through the entire object just from it being passed on, the vibrations, until everyone starts increasing the amount of vibrations and therefore increasing the amount of energy they have, and we see that as heat. Okay. So that is the process of conduction. Basically, only works in solids because in solids, that's when the particles are fixed in their positions and touching each other. And it's all to do with these vibrations passing on from neighbor to neighbor until the whole thing is heated up. Now, we're going to move on to this key phrase that sounds quite complicated, but if you break it down, it is quite simple. And this phrase is thermal conductivity. Okay, thermal conductivity. Basically, you can think of thermal conductivity as how good an object is at performing conduction. Or I could say, even better, how easily / effectively an object conducts heat. Because this process that we just talked about, it's not going to happen at the same exact speed for every single solid. Some solids are just better at doing this than others, especially metals. Typically metals are a lot better than doing this than non-metals. So we notice this, In terms of like materials, engineering, designing products, we notice the importance of being able to recognize that some materials are just better at conducting than others. Because, it's important for us to know this because all of our designs with like everyday objects revolves around this, right? Like what we choose to make a pan with depends on the thermal conductivity. We're not going to make a pan with made out of like, I don't know, wood, even if we make it so the wood doesn't catch on fire, because like wood wouldn't be very good at heating up effectively. So all of our designs for everyday objects is based off of thermal conductivity. How good is this going to be at transferring heat? How good is this going to be at doing what we are looking to do? So we divide all of these materials into two broad categories, two general categories. Obviously, within those categories itself, some would be better than others. So these two categories are, we can call things either a thermal conductor or a thermal insulator. So thermal conductors, typically objects that are good at conduction. And thermal insulators is the opposite, objects bad at conduction. One common misconception that I want to correct, because some students might get sort of confused by this, is that when I say like thermal insulators are bad at conduction, that doesn't mean it's a bad thing, right? Because sometimes we don't want conduction. Sometimes we want conduction, sometimes we don't want conduction. So it all depends on when we're designing something, what do we want? Are we going to pick a conductor for this, or are we going to pick an insulator for this? So examples of conductors are metals, and insulators are typically non-metals. So I'll give an example. Let's say that we are taking something out of the oven. Well, our baking tray is probably going to be made out of metal because we want it to conduct the heat really, really well to get our food to cook, right? But when we take that baking tray out of the oven, we're not going to, put a metal glove on, because then the heat will just pass right through our metal glove and then burn us. So we want a thermal insulator to cover our hands. In that case, we use like oven mitts or non-metals in that case. To protect ourselves from the conduction, because non-metals, even though they do conduct, they are very, very, very slow at it, therefore making it a lot easier for us to design products with that in mind. Okay? So, sometimes as well, is we don't actually even want heat to be able to be lost. Like if you think about, for example, a house during the winter time, we have the heating on, inside of the house is nice and warm. Well, we don't want the heat to escape our house, because then that means that we just have to increase the amount of times we use the heater, increasing our energy bills, and it's also bad for the environment, things like that. So sometimes there are things like unwanted heat transfers. And what we've come up with is basically being able to work out ways we can reduce we can reduce energy transfers. So like if you think about the insulation between your walls, it's that yellow fluffy stuff. Some of you guys might have seen it before. We use that to reduce heat transfer. So there are three main things that contribute to how fast we lose heat. First thing is a temperature difference. If the temperature difference is really high, like for example, let's say that it was 25 degrees inside your house and it's like sub-zero outside. Well, your house is going to lose heat a lot quicker than if it was 25 degrees inside and 21 degrees outside. If the difference is very, very small, it's not going to lose heat as fast. Whereas if the difference is really, really big, you're going to lose heat a lot faster. Now, you can actually like see this in daily life. Like for example, let's say that you touch something a little bit colder than you, like touching the table or something. Your hand would be slowly losing heat to the table through conduction, slowly losing heat energy to the table. Now, if you touched an ice cube, you would feel yourself losing heat a lot faster, even if your body temperature started off the same, because the temperature difference is higher between the table versus the ice cube, the faster the heat transfer is going to be. And the closer the temperatures are together, the slower the heat transfer is going to be. So, temperature difference makes a huge difference. A lot of the times we can't really help that because, you know, the outside weather is the outside weather, but it is something that we can keep in mind. And this next point, you guys might already have this in mind as well, because it is a little bit of common sense, the second point. But if you have something thicker, that's probably going to mean that heat doesn't get lost as quick. So thicker insulation reduces heat loss. The reason why I say it's common sense is because you experience this every day, right? One thing that I want you guys to really understand about physics is that none of these concepts that I'm teaching are unfamiliar to you. None of these concepts are things that are completely outside of the realms of your experience. You guys, just from living your life, know that if you put on a thin jacket, you're going to start feeling colder because you're going to be losing heat a lot faster to the environment. But if you put on a thick jacket, you're going to be losing heat. Like you're going to feel warmer because you're losing a lot less heat. That's just something that you experience every day. So when it comes to reducing heat loss, if we have like a thicker material to insulate you, that's going to be more effective than something that is thin. And that's not to say that thin materials can't insulate. It's just one factor is if you have the same type of material, the thicker the better. Now, the final point is what we just talked about. Thermal conductivity is entirely based on the material. So it's a property of material. How fast is it at conduction? So if something conducts heat a lot quicker, it's going to lose heat a lot quicker because heat passes through it more quickly. So, for example, if like our houses were made out of metal, we'd be constantly losing heat all the time because metals are very, very good conductors. So if it's cold outside, the heat's going to pass through that metal a lot quicker than with a non-metal. So having a metal house is just a bad idea in general because you can't really control the heat flow then, as metals have a really, really high thermal conductivity. Okay. So that is basically the end of conduction. I'm going to move on to the next topic now. So I just want to make it clear. Conduction happens in solids, all to do with vibrations where a particle gets heated, passes on its vibrations to other particles that are nearby it. They pass them on until the whole object is heated and the heat is transferred through. Some objects, though, are better at this process of conduction than others. The ones that are really good at it, we call conductors. The ones that are quite bad at it, we call insulators. And depending on what we want, the end result that we want, we might choose conductors, we might choose insulators. All depends on what product we have. And if we want to reduce heat loss, we can think of reducing heat loss in different ways. We can think about it in terms of a temperature difference. Higher is going to be a faster heat transfer, so we want to reduce temperature difference as much as we can. Thickness, if we have thicker insulation, that'll reduce heat loss. And with thermal conductivity, if we don't want heat loss to be reduced, we're going to pick a material with a low thermal conductivity, so an insulator. Okay. So this next bit here that you're going to find in the booklet is a required practical. Unfortunately, we obviously can't do the required practical. It can be something that you do at home though, but the general idea of this required practical is just like seeing how different materials are better at insulating. And the way it works is you fill up like a beaker or like a cup of hot water, wrap something around it, and then see how long it takes for it to get to a certain temperature, or say after 5 minutes, what temperature is it at. Do the same but with a different material wrapped around it, and then just see what material is better at keeping the heat in and what material isn't very good. So it's basically just testing different materials and seeing how good they are at insulating by checking the temperature of some hot water, seeing how low that temperature dropped. Okay. Now, at GCSE level, for some reason, we don't really need to talk about conduction very much at GCSE level. So, when it comes to conduction, we're looking at solids. Convection, we're talking about gases and liquids. But like I said, we don't need to really go into detail about that. We're going to move on to radiation now. Now, this bit here, radiation, this is triple award. So if you are not triple award, you can finish now, and we have some practice on the website. But if you are taking triple award or taking triple award next year, please make sure that you're still watching the video, because this is going to be relevant to you. So, infrared radiation then. Right. In terms of what radiation is, because we talked about how conduction was solids, we talked about how convection was liquids and gases, well, that doesn't leave much room for there to be a third type of heat transfer if solids, liquids, and gases are all taken. Infrared radiation does not need to use particles to help it transfer its heat. Instead, what it uses are waves. Specifically, something that we call electromagnetic waves. Electromagnetic waves, you're going to go into more detail about this in a later topic, so don't worry too much right now at this stage about knowing everything about electromagnetic waves. But basically, it's just a family of waves, and that's it. It's basically just a family of waves, not particles. Now we have radio waves, microwaves, visible light, ultraviolet, X-rays, gamma rays, all fall under this category. We call them electromagnetic waves. And infrared radiation is also one of those waves. So infrared radiation, basically heat gets transferred through waves. Okay, so instead of it passing from particle to particle, you just have a wave transferring energy. Heat, energy transferred through waves. And this all means that basically it can travel through what's known as a vacuum, which is basically empty space. So if you think about like the sun, for instance, in between us and the sun, okay, is our atmosphere, but then like after that, it's just empty space. It's outer space then. So there's no solids out there for conduction to happen. There's no liquids and gases out there for convection to happen. Most of what's between us and the sun is just empty space. So the only type of heat that can be transferred through outer space is infrared radiation, because it's the only one that can travel through empty space, through what's known as a vacuum. So when you go outside and you feel the heat from the sun, you're feeling the sun's infrared radiation that came all the way from outer space, all the way from the sun, onto you. I think that's actually pretty cool if you think about it, how far the heat has traveled in order to get to you. But that is a side note. But the idea is infrared radiation, it is waves. And because it's waves, just like light, we can emit it, so release it, and also absorb it. And it's important that you know what I mean by emission, or emitting something, and absorbing it. So emission is basically releasing / giving off. So if something was emitting infrared radiation, that means I'm saying it's giving off infrared radiation. And all objects with some heat have this. Emit. I'm going to write IR for infrared radiation. So, for example, you have some heat. You are, even though you don't feel it, you are giving off. So you are, even if you don't feel it, you are giving off some infrared radiation. That's how like infrared cameras work, basically. It detects infrared radiation. So a person, you can actually see the infrared radiation that's given off by people. And that's why, like, you know, you can be able to see in the dark with it, because you're detecting heat signatures then. And the higher the temperature, so higher the temperature, the higher the IR emitted, higher the infrared radiation emitted, basically. Now, when it comes to absorption, all that means is taking in infrared radiation. That's all absorption means. So if you're absorbing infrared radiation, I'm saying that you're taking in infrared radiation and then your temperature is rising. Now, if something's temperature is not changing, then that means, and like if you think about it, you're giving off infrared radiation all the time. Well, if you're constantly giving off infrared radiation, your temperature is going to keep dropping lower and lower and lower, because you're going to keep giving off heat. And eventually you won't have any more heat to give off. Well, that doesn't make sense. We're not just constantly giving off heat until eventually we get so cold that we die. So the reason why our temperature stays the same is because we are giving off heat, we're emitting infrared radiation, but at the same time we're also absorbing or taking in infrared radiation just from the heat around us or heat from the sun. So when you have emission and absorption going at the same rate, then that's why like temperatures aren't just dropping to sub-zero as it keeps giving off infrared radiation. You just have to keep in mind that we're also absorbing it as well. Okay. So I would say we should go on to a bit of practice now. If you go on the website, Let me just quickly just check that it's up there like I would like. Yep, it is. Great. If you go on the website, you should see the energy transfer by heating section along with the booklets there. Remember, feel free to type things into the Word documents instead of the PDFs. I have the PDFs up there just in case. And there's a worksheet under thermal conductivity. So with this worksheet, it's basically just checking your understanding of data. So, for example, question 1, the graph shows how the temperature will change inside rooms in two identical houses that have walls made from the same material. However, the houses have walls of different thicknesses. Now, you see a graph where temperature is dropping over time. Have a think to see which one is probably the thin wall and which one's probably the thick wall. This is testing your knowledge of how thickness affects rate of energy transfer and being able to read a graph. Now have a think about the very thick wall part and then fill in the gaps in the paragraph using the table of information. And by that I don't mean the table is not going to be a word bank. The table is just helping you fill in the sentences. Okay? So that's the main thing. So I'll put the answers up to those in a little bit, but that should be it for today. This will be uploaded for anyone who has not been able to get access to it. And even if you are late in watching it, if you have any questions or if you don't quite understand a bit, feel free to send me an email or leave me a comment on Show My Homework, and I'll get back to you as soon as possible. All right. So have a good day, everyone, and I'll see you soon.